Hello. Over the last few weeks, I tried to create a model that imitates the spread of COVID-19 in the UK. And as you can see on my graphs here, I came up with some quite exciting solutions. These are the real data of the spread in the UK of new cases, and this is the output of my model. And I will explain my model now, and you can trust me. I'm a physicist. What are the key characteristics of my models? First, I follow the SIR model, which is the standard model of epidemic spread, but I use discrete mathematics and I base it on social behavior. Now, to my knowledge, there is no good model around like that. Um, my model allows for easier calculation modifications because of the discrete mathematics and the fact that I use a spreadsheet. And but on the other hand, it gives me a lot deeper insight into the actual spreading mechanisms within a society. What are the social factors that are used? This is the number of people you meet on a weekly basis, the behavior patterns of people, so festivals, holidays, term breaks, how do they behave, and the reactions to government measures uh, during the pandemic. And these measures, they were quantified. They are quantified in my model. I used two groups which were in a ratio of 90% to 10% of them. The 90% of the population were the adults and very young children, and the 10% were secondary school children. The reason that I use those two groups is that their social behavior is by necessity quite different. Whereas students, they had to go to school, they had to go into classrooms with 30 other students around, or before, or they were also in a school with up to 1,000 other students around. Whereas adults, they quite often had a chance to stay at home and to work from home. And if they went to work, they could decide and better control their own risk factors. Also, they could control things like, will I go shopping myself or will I do online shopping, etc. Now, my model assumes that the groups affect each other, also something that's, so mathematically speaking, is convoluted and is something that I think reflects very much what's going on in the real world. And it's also in line with prior socio-statistical studies. There are not very many around, but I found a few and I tried to integrate this into my model. Now, one important part is that this is an a priori model. That means this is not a model where I simply use the data and made a line of best fit. It's something you can easily do. You could download a math software, uh, make a line of best fit, and then create a model out of this. It is not like that at all. It started from first principles. I wanted to quickly recap the SIR model. So this is the standard epidemic model, which has three differential equations where you have susceptible, the ones that can become sick, the infected individuals, so the ones who have the sickness, and the removed ones, the ones that either became healthy again, or, and they cannot be infected again, or unfortunately, this also includes the ones that died from the infection. N is the total population, and then you have these two parameters which connects the susceptible one to the infected one. So basically, how many of the healthy people gets infected, and this parameter, the gamma, which tells you how many of the infected people get removed in a certain time frame. Okay, so what did I do in my model? Well, here I had 60 million people, adults and small children, and 6 million uh, secondary school students, and they have different numbers, sort of base numbers for how many people they meet over a week. Now, this number of people tells you over the week how often you meet people where there is a chance that you can actually get infected. You will, of course, meet a lot more people, but if somebody is more than 2 meters away, there is no chance of getting infected. Okay, this is one thing. The other things that I put into my model is measures from the government, as you can see. For example, here in this week, the tube were closed, then there was the lockdown, the schools were closed, then there were Easter, then there were slight ease of restriction, etc., etc. So what I did is that over the first 8 or 10 months of the period, so I used the data and my model to standardize my parameters, and then I use the same parameters for the next 4 to 5 to predict how the infection would spread. So the first 8 to 10 months were used to optimize my parameters or the relationship between the groups. And then afterwards, I used it and tested as a forecast model. And I even went so far as to forecast the very last 3 weeks, in case there is another week, the very last 4 weeks, where I didn't know it all. And as you can see here, as I showed already in my PowerPoint, the results were very satisfactory. There is one consistent difference between my model and the actual data, and is that my absolute values are higher. And the reason is that I included a hidden infection rate of about 50% on top of the infected cases reported, which seems very plausible and is in line with also some university representatives and government representatives assumed at various times. Most importantly, using this 50% hidden infections created the best fit for the two lines. Okay, so what are the checks? Okay, so what are the checks that I used that my model is accurate and represents the real world? Now, one thing was plausibility checks. For example, how many people you actually meet. I used some minimum value and some maximum values. Another one was lockdown. Make sure that lockdowns, the numbers and parameters in lockdowns are consistent. Why? Since during those lockdown situations, the decline of infections was very, very steady. So there were not huge up and down. It declined very, very steady. The gradients was very straight, which helped me to optimize the parameters. I made sure that the parameters in school closure between school closure times are consistent. I also made sure that the ratio between two groups are taken into account. There is quite a big variation in the proportional infection rate, in the ratio, the proportional ratio between the infection rates over the year. But I made sure that in the boundary that they don't go over certain minimum or maximum values, which are totally implausible. I made sure that the hidden number of infections were kept appropriately constant over the whole time. And I also made sure that major logical consistencies were observed over the period. So there were several autumn bubbles, and I used similar parameters during those bubble times. So these were measurements from the government. So what are the analytical results of the model? Now, the first thing is if group 1 is kept consistent, so they behave very consistent over the whole year, but group 2, sometimes they have to school, then they don't have to school. Group 2 can have a very, very dramatic effect and change the infection rate by a huge amount, although it only makes 10% of the total population. So group 2 is a main factor despite being so small. The other thing I observed is lockdown leads to not only less contacts, but also more cautious behavior. And why do I know that? Because I had to put lower infection transmission rates into my model in order to make my model consistent during those times. It also shows that the effectiveness of government measurements vary greatly, and it is very sensitive to individual group behavior of groups, which is, of course, on one hand very plausible, but maybe a little bit surprising on how strong these effects can actually be. Now, how reliable is the model? I think the ansatz, which means the initial relational assumptions, prove to create correct results. The relational parameters, so the constraining factors that I use, work well. within plausible boundary conditions, so sort of minimum and maximum values that make sense. The adapted starting on the relational parameters create a very good fit with the real data. And one other important thing is, again, the model is not created from finding lines of best fit. It's only created by using assumption and then parameters between the different groups. And they create then this very good fit. So what are the results? 20% plus minus 5 of secondary students have had the virus already, and 10% plus minus 2% of the adult population had it at this point in time. The pupils had a major effect on the large spike last autumn, and I think this is, I'm very convinced of that, and I would give it a 95% reliability factor. The spread of the virus in schools cannot be confined. There is not enough bubble factor to actually contain the virus. The pool of new pupils is still too small for a group immunity. 25, even if it was 25%, is not enough at this point in time. And open the schools in April will create a new spike, and I would give it a sort of 45% chance, or allow only for a flat infection rate. So it will sort of level out, but will not go down enough, even if you use testing and jabs. Okay, what are the measures that you could take? Keep 2 tests per week for students, jab them as quickly as possible, along with the rest of the society, to stop the virus quickly. Either close the schools again, or alternatively, what you could do is keep the parents of students at school in lockdown. So those adults that have students at school, they also they keep in lockdown. Doing this, you will bring down the infection to a sustainable level within 1 to 2 weeks. Okay, what are the forecasts? Now the forecast over the next few weeks. Here you see, this is the blue line is the best scenario if you leave the schools open. And as you can see, it will go down, but then it will sort of flatten out. This would be, I would give this 45%. This I would give also 40%. So the worst scenario, the school is open and actually the infection rate, despite tests and jabs, infection rate will go up again. And in case you wonder, where are the other 10%? This is not 10%, this line here. 10% is that the line would go up even more than that, would not be in this range, or there's a very small chance that indeed it becomes even less. But I think this chance that with schools open, that it will go down very, very quickly is very, very minimal. And the gray line is the one when if you keep the schools closed or you make these bubbles with the pen. I also wanted to quickly discuss the model. The model can be easily downsized into counties, or it can do the other way around. You can even use it in other countries and nations. Only the parameters would need to be adapted. The parameters could be further optimized, similar to what is happening in artificial intelligence via optimization software programs, which would take 1 to 2 months. More correlation factors can be taken into account, and it could. But one thing where I'm very sure it could be turned into an excellent epidemics control tool for governments within a very short time. And by very short times, I mean within 3 to 6 months or so. Now, you may wonder, why can you use physics methods to model the spread of a virus? The reason is because the mass and the system behavior is actually quite similar to a few areas in physics. One of them, maybe the most known one, is fission reactions, so atomic reactions in nuclear reactors or atomic bombs. In a nuclear reactor, you have a neutron that hits a uranium atom, and this releases another 3 neutrons that again hit 3 more uranium atoms, which again releases 3 neutrons. So this is a sort of typical chain reaction. And each time you create some energy in this. And in order for this not to get out of control, you have these control rods. And if it does go out of control, either your nuclear reactor explodes, or if you do it willingly, then you can create an atomic bomb with this. Okay. And last but not least, I would like to refer to some earlier videos of mine. Look under Physics Corridor use the quotation marks on YouTube, and you will find some other videos of mine, some about these topics. Bye for now.